Now remember table A2 and Excel tell us the cumulative area from the left. It worked out for that previous example because we wanted a bone density score less than 1.27. Let's try this example now. So using the same bone density test, find the probability that a randomly selected person has a result above negative 1.0. Now, it doesn't really matter for our statistics class, but a value above -1 is considered to be in the normal range of bone density readings. Let's solve this now. So using Excel or table A2, we know that it's designated to apply only to cumulative areas from the left, so values below that given z-score. Our z-score here is -1.00. If we looked in the table or we used Excel, as we just talked about, for a z-score of -1.00, we're going to find an area value of 0.1587. Using Excel, remember we're going to use norm.dist function. The first number here is our z-score, or -1. The second value is our mean, or 0. The third value is our standard deviation, or 1. And then our cumulative value, or our fourth value, is also equal to 1. Clicking enter to this, we get a value of 0.1587. Also looking at table A2, going over to the negative z-scores, finding 1.0, then going to our hundredths place of another 0, we'll also find this value of 0.1587. Now we're familiar with complements. So we know that if this all totals up to 1, which it does, the area under this curve, then this cumulative area to the left plus what we really want here will equal up to 1. Remember, what we really want is to find that a person has a result above -1.00, finding the probability of that. So what do we do with complements? We're going to take this value that we know, which is the complement to the value that we actually are asked about in the question. We do 1 minus that value to get our true answer. So here, for example, we found 0.1587. We take 1 minus that value. That result is 0.8413. So that area is our probability. Then that probability is that we randomly select a person and they have a bone density value greater than -1.00. So we know how to work with Excel and table A2. Because those give us our cumulative area from the left, we can still figure out the cumulative area to the right. We just take 1 minus the value that we get for the area or the probability. So importantly, we need to read the question. If it says some value less than a certain z-score, we can use the value from the table or Excel as is. If instead the question says a result above some given z-score, then we need to take the complement, or 1 minus the value we get from Excel or using that table, because those values from Excel and the table will give us our cumulative area from the left. Let's talk about the interpretation again more explicitly. We know this connection between probability and area, so we conclude that the probability of randomly selecting someone with a bone density reading above -1 is equivalent to 0.8413. It's not the area to the left that we report, it's the area to the right of that z-score. In percentages then, we could say that 84.13% of people have bone density levels above -1.00, where this is considered in a normal range for bone densities. Okay, so far we've talked about cumulative areas to the left, cumulative area to the right. Now we'll do an example with getting the probability or the area between two given values or between two given z-scores. So here, a bone density reading between -1.00 and -2.50 indicates that the patient has osteopenia. We're going to find the probability that a randomly selected subject has a reading between -1.00 and -2.50. For the solution here, we first want to know the area to the left when z is equal to -1.00. We know how to do this with Excel. We know how to do this with Table A2. I highly recommend drawing out examples like this. So the area to the left, when z is equal to 1.00, where the z-score would be here, pictorially, this means that this area is 0.1587. Next, we need the area to the left when z is equal to negative 2.50. We can use Excel, we can use Table A2 to get this value here of 0.0062. Drawing this out pictorially, we have our z-score here of negative 2.50, then this small area is 0.0062. If it wasn't clear yet, I did want to mention that we have our mean value of mu, or 0, right here, where this is at its maximum value. Then negative z-scores will be to the left of that mean, and positive z-scores will be to the right. Okay, I wanted to mention that explicitly before we move on. Then to solve this problem, we need the area between z is equal to negative 1.00 and z is equal to negative 2.50. We can do this algebraically. It's also always good to draw a picture. So here's our z-score of negative 1.00. We know this full area here. Here's our z-score of negative 2.50. We know that small bit of area there. So then to find this area between, we're going to take 0.1587 minus 0.0062. This gives us an area value of 0.1525. As you're going along with this, I definitely recommend checking these values using Excel or Table A2, or even both. Now for the interpretation, we're using this connection again between probability and area. So we conclude there's a probability of 0.1525 that a randomly selected subject has a bone density reading between negative 1.00 and negative 2.50. Remember, because of this connection, we found the area, therefore we found the probability. Why could we do that? It's because the area under the curve for a normal distribution totals up to 1. Where we know from probabilities that that's the total probability where something is absolutely certain to occur is when it has a probability value of 1. For the interpretation, again, using percentages, it's important to be able to go between percentages and decimal values. So another way to say this is that 15.25% of people have osteopenia because this percentage of patients have bone density readings between negative 1.00 and negative 2.50. Now we just did this example to find the area between two given values. Generally, when you're doing this, we know we can find the difference between those two z-scores by finding the area under the curve for the first and the area under the curve for the second, and then we subtracted those values. It really isn't worth memorizing anything here. It's better to draw out and picture what's happening. So we draw a graph, shade the desired area, then we get creative to find the area of that given portion by, importantly, working with these cumulative areas from the left. Okay, so there's another practice problem for you on your student outline. You'll also get more practice with this with your MyStatLab homework. Okay, so we've gone through all these important examples so far. There is one other style of question you might see, so finding a z-score from a known area. So we might also be given an area or probability and be asked to find the z-score that corresponds to this area. For example, find the z-score that yields an area of 0.7019. This area is greater than 0.5. That means we're going to be on the side of the positive z-scores.
So I added in this visual to your slides so we can see on the left-hand side, those are our negative z-scores, right? A z-score is how many standard deviations we are away from the mean. So negative 2.50 z-score, that's 2.5 standard deviations away from the mean, but on the negative sides, the left-hand side of the curve. Then negative 1.00 is not as negative, so that's just slightly to the right of negative 2.5. Because negative 1.00 as a z-score means we're exactly 1 standard deviation away from the mean. Then on the right-hand side, those will be our positive z-scores, right? Are we 1 standard deviation away from the mean, 2, 3, etc.? And remember, these z-scores work out in this way because we're working with a standard normal distribution where the set of data has a mean exactly equal to 0 and a standard deviation exactly equal to 1. Then as far as the area under the curve, we know the total area under the curve is 1. Then on the left-hand side that corresponds to the negative z-scores, that area is between 0 up through 0.5, right? Then on the right-hand side of this graph, because it's symmetric, then the positive z-scores correlate with areas between 0.5 and 1. So that's how we're solving this next example here.
So here I'm on the page with the positive z-scores, again because our area value is greater than 0.5. Let's find this area value. Okay, so there it is, 0.7019. How do we find that corresponding z-score then? We're going to look at this left-hand column, so 0.5. Then this first row for our hundredths place. So the corresponding z-score here would be 0.53. Okay, so it's not too bad. You'll want to look at your table. Be very careful about matching up this row here with this column here. Okay, so far we've kept in mind this cumulative area from the left. If we're asked about a cumulative area to the right or a number greater than, we can find the complement of that cumulative area from the left. In other words, we're going to draw a bell-shaped curve, identify the region under the curve that corresponds to a given probability. It changes the problem a little bit if that region is not a cumulative region from the left. We know that instead, we can work with a known region that is cumulative from the left, and then take the complement of that value. For example, with bone densities, if we wanted to know the probability that a patient has a bone density value greater than negative 1.00, we'd first find this area here, this probability that's cumulative to the left, using a given z-score, then take 1 minus this area to get our true probability of 0.8413. Remember, this 0.1587 is what we get using our table or get using Excel. Then we need to think through and know to take 1 minus this value when we're asked specifically about the probability of getting a value that's greater than our given z-score. Let me show you explicitly how we do this with table A2. Now, we're given a z-score of negative 1.00. We're going to find negative 1.0 in this first column. Then the hundredths place is also a 0, so 1.00, negative 1.00. We go down to this corresponding area or probability value, it's 0.1587. Then we know for the complement, we take 1 minus 1.587. We get our true probability of 0.8413. We should be comfortable using the table and performing a calculation in this way. Really pay attention to what the question is asking us. Okay, so we're getting comfortable using the table. We're also getting comfortable using Excel, of course. Now, I showed you how to use a table to find a z-score given a known area. You locate that area, and then you find the corresponding z-score. But can't I use Excel for that because I really love Excel? Well, the answer is yes, you can use Excel for this as well. The function in Excel for this is the normal inverse. So the function is going to look like norm.inv. Using the same probabilities and the same z-score that I just used on the last slide, we're going to go through this example with Excel. So with this normal inverse function, we need a probability value, we need a mean value, and we need a standard deviation value. Fortunately, for normal distribution values, our mean is always 0, our standard deviation is always 1. So we know how to take the complement and solve for either the cumulative area to the left or the cumulative area to the right. Let's say we didn't want to do this. Let's say we were given a probability of 0.1587 or an area of 0.1587, and we wanted to know that z-score. This is where we use Excel with the normal inverse function. We plug in 0.1587 for a probability. We know our mean. We know our standard deviation. So this is when I'm setting up this function. I click enter, then I get an answer. My answer using the normal inverse function in Excel is my z-score. So I took a probability, I took an area, I solved for a z-score directly using Excel. Now we know from the table that a probability value of 0.1587, that cumulative area to the left, has a corresponding z-score of -1. Excel told us the z-score is -0.9998. That's essentially 1. They're very similar, they're slightly different, and that's okay. An important thing to recognize with this normal inverse function is that whatever probability we plug in here, Excel will compute the z-score as if this probability is the area under the curve cumulative from the left. It's always in reference to the cumulative area from the left. Okay, so in summary here, to find a z-score from a known area, we can either use Excel or the table. For all of these cases in this whole section, essentially, we want to keep in mind that that probability or that area value, they're the same thing when we're working with standard normal distributions specifically. And then those probability and those area values that I just mentioned, they always refer to the cumulative area from the left. Let's go through some notation now. Most of what you've seen already in 6.1 and one new way of this notation. So if we have a probability of an event, remember that event will be in the parentheses here, of a z-score that is greater than A but less than B. That's really saying that the probability that the z-score is between the values of A and B. We could also have this notation, the probability of this event, where the event is that z is greater than A. Next, we could have the probability that z is less than A. So this notation here denotes the probability that the z-score is less than A. Here's the new notation now. So this expression of z subscript alpha, it denotes the z-score with an area of alpha, whatever value is in that subscript position, to its right. Remember, this is the trickier case when we have to figure out a probability or an area value to the right of a given z-score. This is the notation that we use for those cases. We'll do an example of this. First, a few more definitions. So for a critical value, for the standard normal distribution, a critical value is a z-score on the borderline of separating those z-scores that are significantly low or significantly high. You know we wouldn't get through a section or a chapter without talking about significantly low or significantly high values. So here it is. The notation for critical values is this expression z subscript alpha. It denotes the z-score with an area of alpha to its right. We're going to use this notation in talking about the critical values and talking about significantly low or significantly high values. Here's our example. Let's find the value of z subscript alpha, where alpha is 0.025. Remember the meaning of this notation here. So this denotes the z-score with an area of alpha to its right. Let's talk through the solution now. So here's our notation again. This z subscript alpha, where alpha is 0.025. We want to know the corresponding z-score when we have an alpha or an area value of 0.025 to the right. We know that with Excel and with our table A2, we need to consider areas to the left. So how do we solve for this? If this is the area to the right, then what would the area to the left be equal to? Well, we can take 1, the area under the curve, minus 0.025. That area then is equal to 0.975. 0.975 tells us our cumulative area from the left. We need that cumulative area from the left in order to find the proper z-score. So when we look at this area of 0.975 in our table, we get a z-score of positive 1.96. Okay, so to review, we can make a figure like this. I think it's helpful. we know that our alpha value, our area value, is 0.025 to the right, given this notation. Using the table, that's not going to help us necessarily. We need to find the area to the left, so we take this total area, 1 minus 0.025. This cumulative area to the left then is 0.975. We can look up this value in our table A2 and find the corresponding z-score of 1.96. Now, because normal distributions are symmetric, it does turn out that an area of 0.025 to the right is a z-score of 1.96. Also, an area of 0.025 to the left corresponds to a z-score of negative 1.96. So now you can start to imagine using these critical values to determine significance. Then these values here to the left of negative 1.96, or these values here to the right of positive 1.96, could reflect that these values are significantly low and these values are significantly high. Now, I know what you're going to ask, can we use Excel? Of course you can. Here's our notation again. So Z subscript alpha, where alpha is 0.025. We want to know the corresponding z-score, where the area to the right is 0.025. Now we need to follow the same reasoning as we did for the table, so we really need to know the cumulative area from the left. Again, we're going to take 1 minus 0.025. We get the same value of 0.975. That's our cumulative area from the left. Now that we know an area or we know a probability value, we can use this normal inverse function in Excel where the probability value is 0.975. Our mean, as always for a normal distribution, is 0. Our standard deviation, always for a normal distribution, is 1. Then we set up our equation like this. We click enter. We get the corresponding z-score of positive 1.96. Okay, now, one last word of caution. When finding a value of z subscript alpha for a particular value of alpha, this notation in itself means that we want alpha, or the area, to the right of a certain z-score. Remember that table A2 and Excel need us to work in terms of cumulative areas from the left, or cumulative areas to the left of a certain z-score. To find that value for z alpha, we're going to resolve this conflict by using the value of 1 minus alpha. For example, if our alpha was 0.1 instead of 0.025, then we'll take 1 minus 0.1, we get an area of 0.9. Then we use this cumulative area to the left in either Excel or our table A2 to determine that corresponding z-score. There are lots of tries on your student outline. As always, let me know if you want to check any of your answers or talk through any of these concepts. I will see you next time for 6.2. Remember to keep up with your MyStatLab homework and, of course, enjoy the rest of your day.